0.5 on linear approximation. Then we're also going to do differentials. And so I didn't assign a lot of problems from this because I know you're working on some difficult stuff, but we'll get to it. The first thing to talk about was this example in the book. They talk about the driving math. I thought this was kind of cool. Well, let's do this first. So here's a really nice picture, okay? And you see that we have a formula here for L of x, and I'm going to jot that down and just make sure that you guys understand where that's coming from. So L of x is going to be f of a plus f prime of a times x minus a. But I don't want you to panic because it's actually nothing new. Okay? If we go to their picture again just for a second, and then we go back. All right, what did their picture look like? They had a curve, and then they also had a line. Now I'm going to use orange instead of red. But that's the picture, right? A tangent line. And what I want, basically, is I want the equation of this tangent line, L of x. Haven't you done that problem like 50,000 times? Find an equation of the line tangent to the curve at x equals a, right? Haven't we done that like a million times? By the way, this curve, we'll call it f of x. And so if I tell you that this is the point x equals a, okay, so I guess my question is, what are the, is that a little blurry, or is that good? Is that off a little bit? I think so. So how do we do this? What's the process? Well, what's the equation going to be, basically? What's the form we're going to use? Find an equation of the line tangent. What do you think? Point slope form. So we think y minus y1 is m times x minus x1, right? Can you fill in anything? Well, we can fill in x1. What's x1? That's a. Right? So that's that. What about the slope? Well, the slope comes from the derivative. And you have to plug in a, right? That's that. And then you get y minus a. So my equation of my line is really coming from the same thing I've done a million times. Does this make sense? That's about it. Okay. So this is nothing new in a sense, right? It's the same formula I've done a million times, and that's what they're getting at here. And so now what we're going to want to do is we're going to want to move along L of x, okay? So, define the linear approximation to be move along the tangent line, okay? And so this is kind of interesting. Useful driving math. Did you guys see this? So I remember my parents doing this when I was in the car because they wanted to know, is the speedometer working or not? Now, really, what were they doing? Probably trying to kill time on a 5-hour trip with a little kid in the car, right? But we're driving. We had to find the mile marker. and then go. And we would time how long it went to drive 1 mile. Okay? And if it took 60 seconds, that means you're going 1 mile per minute, right? So 1 mile per minute would be what? 1 mile in 1 minute, right? Yes, because there are 60 minutes in an hour. So if I multiply, I'm at 60 miles per hour. Okay? But what happens if you go 58 seconds and you're already there? What's that? You're speeding, right? You're going over 60. That depends on the speed limit, I guess. Or what if it takes 62 seconds? Okay? So this little tidbit says, well, look, if you drive 1 mile in 62 seconds, then you can just say, well, it's 58. All right? So here's what they do. They actually derive the formula. And when they work out the formula, they get 60 minus x. And they say, well, there you are, right? So if I'm going 50, if it takes me 57 seconds, okay, so I'm off by 3, I'm going a little faster, the estimate would say I'm going 63 miles an hour. Are you with me? Of course, they actually show you they got this equation 60 minus x using our old formula. Okay? And then quick check 2 is all about that. So that's kind of interesting, I think. So let's look at a couple homework problems maybe. So number 8, for instance, right? Number 8 says, if I travel 1 mile in 63 seconds, what's my approximate average speed and what is the exact speed? Well, the approximate speed would be what? .57 miles per hour. Yeah, it took me 63. But now how do you get the exact speed? Well, for the exact speed, we have to understand kind of where this all comes from. Right? So I guess I could work it out, right? So what I have is I know that x is my speed above or below 60, right? It's how many miles per hour above or below. I know that rate times time is distance. Right? My rate times my time is my distance. So what's my distance? 1 mile. What's my time? Well, I guess it's 57. Oh, we said 63, sorry. 63 seconds. Okay. So my exact speed would be 1 mile over 63 seconds. But of course, I want miles per hour, right? So I could change the seconds. Let's see, there's 60 seconds in 1 minute. And there are 60 minutes in 1 hour. So I could say my exact speed would be, well, 3,600 over 63. Let's see what that is. Pull that over here. $3,600 divided by 63, 57.14 miles per hour. Okay? So I guess the real question is this a good estimate? No. You're only off a little bit, right? So why would you go through doing all this in your head when you can just do that? And that's kind of the point of linear approximation. Okay?
Is this something that I didn't realize I've been doing all the time when driving to and from here?
It's kind of a nice little trick, huh? If you're doing this as your formula, just subtract x. The reason that works is because what it really is a linear approximation. Okay? And again, that'll work as long as I'm close to the value of the point of tangency.
I've been using it to figure out how long it's going to take me to get somewhere.
Sure,
Yeah.
sure. Okay, so let's take a look at another example here, maybe from the book also. Okay, so each of these, let me do one of these from 13 to 20. How about problem 13 is not a bad one to start with. Problem 13. So I have actually let me do 14. I like getting a little trig involved sometimes. 14. So it's f of x equals the sine of x. And they tell me that a is pi over 4. And what we want to do is we want to find f of 0.75. Okay. So this is kind of an interesting problem because I know a lot about the sine graph, right? I know a little bit what the graph looks like. Let me draw a sketch. I think part B actually asks me to draw a sketch, so I'm going to do that. So I know that the sine of 0 is 0. Do you guys know the sine of pi over 4? Radical 2 over 2, right? So somewhere here at pi over 4, I'm at the square root of 2 over 2. So that's pi over 4 and the square root of 2 over 2 is that point there. And of course, if I go all the way to pi over 2, then the value gets up to 1. Right? So here's pi over 2 comma 1. And then it starts to come back down, and then it does this, and then it does that, right? So there's my picture. And what I want to compute, see, I know this because that's a nice radian measure. I'm supposed to compute f of 3/4. Now, where's that on the picture? F of 3/4. Well, which is bigger, pi or 3? Pi's bigger. So 3/4 must be a little bit to this side, right? And so I guess what I'm wondering is what's the sine of 3/4? That's not one I have memorized. Okay? So I want to compute that. But instead what I'm going to do is I'm going to use a linear approximation. And so what I'm going to do is I'm going to move along the tangent line. So there's the picture. And what I will do is I will, instead of doing f of 3/4, I will compute L of 3/4 instead. That will be my linear approximation. You guys follow? Question, is L of 3/4 going to be bigger than the sine of 3/4 or smaller than the sine of 3/4? You can see from the picture my estimate's going to be bigger because the tangent line is above the curve. You see that? It's nice to know that. So I'll know kind of where the error is. All right, so let's compute L of x. So again, we have the formula from above that we said is just really nothing more than, find the equation of a tangent line. So there it is. L of x is equal to f of a plus f prime of a times x minus a. And so I can say L of x is equal to, where it says f of a, well, for us, that's the sine of pi over 4. Correct? That's my a value, is the pi over 4. So a in the book is talking about the point of tangency. You guys see that? Plus. And then it says cosine, no, it doesn't say that. It says f prime of a, but I just gave away. What do you have to do? Yeah, because what is f prime of x? Cosine of x, right? So we need the cosine of pi over 4, which we also know. And then we need x minus pi over 4. Okay? So if I continue to work, L of x is the square root of 2 over 2 plus the square root of 2 over 2 times x minus pi over 4. Okay? And now I'm ready to compute L of 0.75. Okay? So this will be the linear approximation. Let me compute that. I'll use the calculator also. And now I'll compare it to what the sine of 0.75 is. So L of 0.75 would be, let's see. So to speed things up, I'll just write 1 divided by square root of 2, because that's the same as the square root of 2 over 2. Okay. Plus, and then I'll write 1 divided by square root of 2 again. Times, and then open parentheses, and where it says x minus pi over 4, where it used to say x, what am I supposed to put? 0.75. So I'll write 0.75 minus pi over 4. And if I work that all out, I get 0.6821. If I round to 4 decimal places. Okay. And now let me just compare that to what f of 0.75 is. The sine of 0.75 should be something a little smaller. And let's just see if that's the case. Yeah, a little bit, right? You get 0.6816. That's how linear approximation works. Any questions? One thing the book will ask you to do a little bit is they'll ask you to talk about the error. How much error is there? Well, here it's to the thousandths place, right? And we'll talk about percent error. And so you divide. I think you guys have done that probably in a science class. If not, we can talk more about that next time. Okay. But this is the basic idea. Oh, was there anything else I was supposed to do according to the homework directions? Write the equation, did that. Graph the function, did that. Use the linear approximation. Oh yeah, so compute the percent error. Do you guys want me to do that? Okay, let's finish the problem then. So it says do 100 times approximate minus exact over exact, where the exact value is given by a calculator, right? So I guess I can do that, well, here, right, with the calculator. So let's take the calculator out again. And so the approximate value was this one, minus the exact value. Oh, that didn't work. I need my answer minus the exact value. So let me just take the answer I just had, minus, well, again, the sine of 0.75. And then what I'm going to do is I'm going to divide that by 0.75. So take this whole thing and divide by the exact value. So I'll divide by the sine of 0.75. Does this make sense, you guys? Okay. Let's see what I get. Oh, what's that mean? So that means my error. All right, so part D, the percent error for this one is really small. It said, what did it say? 6.42, but that means E negative 4 means times 10 to the negative 4th. So it'd be 0.0006, because it's 10 to the negative 4, right? Oh, but times 100. So I could say it's 0.06% error. That's what I'm looking at there. That's really small. Okay? So, not that you would ever compute the sign this way if you have a calculator. I get that. But this at least is a nice example for giving you an understanding of what linear approximation is really doing. So drawing the sketch, I think, is important. Okay. The other part of the homework has to do with what are called differentials. Actually, let's look at the notes a little bit. Yeah, here. So it says to approximate the change delta y, you can do f prime of a times delta x, okay? That's a fancy way of kind of saying, now let me draw a picture and kind of show you what's going on here. So here, let's draw one of our favorite functions. How about, let's go with y equals x squared. And let me go through this point here. I'm going to say is 2 comma 4. Right. And so maybe I say, well, here's the tangent line. That's okay. I'm gonna do a slightly different picture here. Let's do this instead. Let's draw the graph over again, and let's have a curve, but maybe not so steep. Okay, let's do this. I don't know what the equation of that curve is. I'm just going to say that here is my point, and here is my tangent line, right? And so this is what the book would call a comma f of a, right? And this is what the book would call L of x. I got to zoom out, or you can't see that. There we go, a little more room. So there's L of x. And so the point is, maybe I'm interested in computing this value here. Right? So I want to know what happens when I deviate a little bit from A. So here, let's call this delta x. And then here, what am I going to call that? Delta y. Delta y. Okay? When you use linear approximation, you're not really computing delta y, right? What you're computing instead is this right here, that quantity. Does that make sense? And this leads into the idea of what are called differentials. So the book, we're going to call this little quantity here, we're going to call this dy. And we're going to call this quantity dx. differentials. A little small change in y and a little small change in x. And actually, the nice thing about doing this is then you would say that, well, dy over dx is f prime of a. So when Leibniz used to write this expression for the derivative, he really did mean a fraction. He took a very small quantity over a very small quantity, and that is a slope of the tangent line. And that's really the picture there. Okay? So what we can do is we can now express anything using the Leibniz notation. So let me show you, well, a sample exercise. Did you guys do a quick check like this? I guess you did. No, maybe not. Here, let's do one of these. Differentials. Okay, so let's do 37, for instance. Problem 37 is the problem f of x equals 1 over x cubed. It says we want to express the relationship using differentials, okay? So we're going to, my final answer here is going to be dy equals f prime of x dx. That's how we're going to write it. Okay? Of course, I mean, where's that coming from? That's coming from dy dx is f prime of x. Now, if I want to compute f prime of x for problem 37, well, how are you going to write f of x? First, we'll write f of x is equal to what? X to what power? Negative third. So I could say that f prime of x here, okay? So one thing I could do is I could say that dy dx is equal to negative 3x to the negative 4, right? And so the way to write that using differentials is we say dy is equal to negative 3x to the negative 4 dx. Okay? This is called differential. Well, you know what this is really called? This is called a differential equation. You always wondered what that is? The study of differential equations? It's studying an equation like this. When you see this, I want you to understand another way to write this is just dy dx is equal to negative 3x to the negative 4. Okay? But it turns out that you can write lots of other differential equations. This is just maybe the simplest kind you'll ever see. Okay? And so they figure, hey, while we're drawing all these linear approximations, now's the perfect time to introduce what dy and dx really are. There's something on the graph. Here's a little statement I've seen written in some books that probably makes sense to you. Dx is equal to delta x, but dy does not equal what? Delta y. Right? What does dy equal? Right there. F prime of x dx. Okay. And maybe that explains enough about the picture. All right, maybe one last example. No, not that. Oh, this is kind of nice, yeah. Approximating changes. Let's do 34. 34 says, approximate the change in the magnitude of the electrostatic force between two charges. So R here is the charge. 20 m. Wonder what m is. It's not meters, is it? Not for a charge. Well, now my lack of physics is showing through, right? Huh. So what would be a unit of charge? Let's get the... Well, let's...
No, meters.
Meters? Really?
Yeah, the distance between.
Unit of charge. The coulomb. Yeah, that seems better. So why are we talking about M? M. Oh. Meters per Q. M per Q. Mass to charge ratio. Kilograms per coulomb. One can deduce the mass of a single atom. Is that what they're talking about? No, I don't know. Yeah, I don't like that one. I don't know enough about it, guys. I think I'll stick to something like 31. How about that? Last example of the day, maybe? Okay? So if they say to approximate the change in volume when a sphere changes. So yeah, you blow up a balloon, right? It's a sphere, let's say, or a basketball. And you want to know how much volume is in there, right? And so that's easy. We can do volume is 4/3 pi r cubed, right? Yeah, I have like 1 minute left, I realize that. Okay, so my volume here, this is number 31. My volume is 4/3 pi r cubed. And so my r, 5, right, cubed. 125 times 4 is 500 over 3 pi, right? So 500 pi over 3. And so I could get what that is, I guess, with a calculator. So 523 and a half. And these are cubic feet. That's a big basketball, that's for sure. Well, 5-foot basketball. It's more like a medicine ball. Right? Enormous one. Okay. So what happens if there's an error and you're at 5.1? This would give me the exact value. But if I want an approximate value, I could do the following. I could say, look, V is 4/3 pi r cubed. dV is, if I take the derivative, 4 pi is a constant. The reason I got rid of that 3 was because bing, I brought the 3 down. It's 4 pi r squared dr. And so the change in volume is equal to 4 pi 5 squared times 0.1, because that's how much the radius changed. So I get 100 pi times 0.1 is 10 pi. And so that's kind of interesting, because if I try 10 pi, I get 31.41 is how much it would change by. And that's an approximation to what you'd get if you did the exact volume. We're at time, guys. We got to get out of here. So.